Is there another copy of you watching this video, deciding to press pause without finishing this sentence while you are watching on? A person living on a planet called Earth, with misty mountains, fertile fields, and sprawling cities, and a solar system with 8 other planets. The life of this person has been identical to yours in every respect. Until now, that is. When you watching on signals that your 2 lives are diverging. Yeah, I did not come up with that. This is how MIT professor Max Tegmark began one of his leading papers in astrophysics in parallel universes. Except, you know, it was about reading his article and not about watching this video. Fun fact, he also really likes puns. Why do I know that, you might ask? Well, it was actually because he was my freshman year physics professor. So if none of my jokes are funny, I'm just going to blame it on him. However, he can confirm that although I'm using Minecraft to explain these topics, this is our understanding of physics at the moment, no matter how out of a video game they may seem. I'm sure this near identical universe sounds impossible. But what if I told you that not only is there that one copy of you universe, but an infinite number of copies of you, all living out their lives in the infinite number of ways you could have lived out yours? Kind of makes 14,605 seem like a grain of sand in comparison to infinity. Now, in order to understand where all of this comes from, we have to start with the father of physics himself, Newton. One of the most fundamental things that Newton determined was that all objects operate according to the same rules of physics, no matter what side of the world you're on. Basically, he determined that if an apple fell on your head at the top of a mountain, it would hurt just as bad if an apple fell at your head at sea level, after an apple fell on his head. Or, you know, so the story goes. Minecraft actually nodded to this in their 1.1 update when introducing apples.
Fancy an apple? They fall from trees now.
Newton would be proud.
Except then, you know, not too long ago we realized that this was wrong, and our most fundamental understanding of physics in the universe was also wrong. So, sorry Minecraft. In actuality, physics operates according to 2 sets of rules. Classical mechanics, which describes the behavior of macroscopic bodies, and quantum mechanics, which describes the behavior of microscopic bodies. See, it's kind of like econ, but fun. The way we figured this out was through the double slit experiment as introduced by Thomas Young. To start our experiment, if you set up 2 slits and shot a bunch of arrows at the screen in our macroscopic world, there would be a distribution like this, which, you know, makes sense. Then, if you were to put a wave through those slits, it would cause this diffraction pattern from interference, where there's a bunch of places where the wave cancels, creating valleys, and other places where they add and create peaks. Here's where it gets interesting. If you were to go into the quantum microscopic world, and then pretend that our arrow presents a singular particle, what would happen when you sent it through the slits one at a time? You'd expect to get this picture, right? Well, that doesn't happen. We actually get the image produced from waves. This means that the light particle must be interfering with itself. In other words, it's going through both slits at the same time. Here's where it gets even crazier. If you were to put a sensor here, thank you 1.19, in order to figure out which of the 2 slits that each particle is going through, you get the first picture with no interference. What's going on here? Now, this experiment proved that particles at the quantum level have both point and wave-like properties, meaning that they don't follow our classical mechanics. Then, not too long later, the function that actually describes that wave was defined by this guy named Schrodinger, coined Schrodinger's equation. Scientists aren't exactly known for their creative naming abilities. Now, here's the problem. Despite all of the math working out, we never actually observe the wave function. Whenever we try to measure it, we record a single point in space, or the wave breaks. No one knew how to interpret the wave function until this guy named Max Born came along. See, the wave function has an amplitude, or height, as defined by a complex number, otherwise known as a real number plus an imaginary one. Now, math is kind of cool sometimes. Okay, listen, sometimes it's cool, I promise. And it turns out that in order to turn a complex number into a real number, all you need to do is square the magnitude. It works out every single time. Don't ask me what that means in your context though, because that does change. Anyways, Born saw this value and came to the conclusion that the square of the magnitude of the wave function is the probability of the particle being located in that position. The crazier part, it wasn't even in his paper at all. It was in the footnotes. There's a joke in there somewhere. Okay, I just can't find it at the moment. Everything we just proved is this idea of superposition, or the concept that at the quantum level, matter can exist in more than one place at one time. like a wave. Basically, instead of the electron orbiting around its nucleus, it more surrounds it all at once, with a probability of it being located higher in some places than others. Then when you go to measure its location, the wave part collapses or breaks, and the point-like particle appears. Now, Einstein specifically hated this interpretation, mainly because it introduced the concept of probability and statistics into physics. Imagine throwing our apple and just not knowing if it had a probability of not following gravity that day. Not only did Einstein hate this, but so did everyone else. But like, besides everyone else, most notably Schrodinger, he hated this interpretation of his own equation. No one ever talks about the fact that Schrodinger created Schrodinger's cat to disprove the very thing that's used to prove nowadays. Not like that's ever happened before. I'm looking at you, Dare. Anyways, Schrodinger hated this interpretation so much that he started killing cats in his brain. So that's what we're gonna do in Minecraft. Okay, listen. Schrodinger's cat can be defined with a simple model. If we go back into our quantum world, Schrodinger essentially took a bomb that had a 50% chance of exploding along with a cat, and then placed them in the same box. Now, the box had no indicators of what was happening inside. Completely opaque, soundproof, etc. In Minecraft, it seems like it was coded to avoid this very scenario from happening. I mean, cats scare away creepers? Come on. Of course, it's also very hard to replicate chance in Minecraft. But luckily for us, and unluckily for our cats, I've coded it so creepers now have a 50% chance of exploding when they see a cat, and a 50% chance that they'll run away. If we were to do this experiment, according to Bourne's interpretation of physics, what is the cat? Alive or dead? It exists in a superposition of both alive and dead until we measure it. Turns out the glass isn't half empty or half full, it's half empty and half full. See, it's funny because it's a quantum joke and a chemistry. Okay, listen. However, when Schrodinger conducted his thought experiment, he was like, see? I've never seen an alive and dead cat, and you've never seen an alive and dead cat. And if you have, then there's probably something else going on. So therefore, this interpretation of physics must be wrong. But what Schrodinger didn't realize is that the cat is both alive and dead. It's alive in one universe and dead in another. What he stumbled upon here is entanglement. Essentially the idea that whenever an object in superposition becomes entangled with its environment through measurement, the universe splits. Now, how do we prove entanglement? By killing turtles in Minecraft. Let's change our experiment slightly. Instead of having one box, we'll have two, and instead of there being cats, there are turtles. No reason. If we were to perform this experiment in our macroscopic world, meaning the creepers aren't entangled, and then we recorded the results, we'd eventually get that there was a 25% chance that both turtles survived, a 50% chance that one of the turtles were dead, and another 25% chance that both turtles died. Now, let's go back into our quantum world and have the states of our two creepers entangled, the same way that electrons get entangled with each other whenever they're in close proximity. Here's the crazy part. The two scenarios where both turtles died and both turtles survived never occur. Meaning that without fail, one box has the alive turtle and the other one has the dead one. It doesn't matter which one is alive or dead or which one we measure first. It's not predetermined. Somehow, these creepers, or electrons, are communicating faster than the speed of light, which, of course, is impossible without entanglement. You may believe that this is all theory, but it's been tested. Two entangled electrons, both in a state of superposition, where they both have quote-unquote up and down spin simultaneously. Okay, don't question it, electrons are magical like that. Will always have opposing answers after being measured, even if there's no way for information to pass between the two. Now that we've proved entanglement, how do these tie back to alternate universes? Whenever an object in a superposition state becomes entangled with the environment, it undergoes what is called environmental decoherence. Okay, listen, I don't know how to say it. Please don't flame me. Otherwise known as a splitting of the universe into two slightly different copies. This theory is called many worlds, as introduced by Hugh Everett. This also removes what Einstein was so skeptical about: probability. Every outcome happens 100% of the time, just in different universes. And if we remember from before, whenever we attempted to measure our Schrodinger equation, it would break. But if we take into consideration all of the other universes, the math actually works out. We're no longer getting a breaking of the Schrodinger equation, meaning that according to math, this is how our universe functions. And as crazy as it might seem, although we have no way to measure it now, we might be able to in the future. Now remember, this is just a theory, and all of these big sciencey names are like fighting over what's right. It's kind of like physics trauma, and a lot of them actually just don't care. But overall, there's just so much we don't know. We don't know how often the universe branches or how often superposition occurs, but what we do know is that it happens often enough that it might as well be infinite. There are 5,000 radioactive atomic nuclei in your body in a superposition of decayed or not decayed per second. Then they continue to interact with their environment, become entangled, and the universe branches. Even the math for energy works out. I don't know how to explain it, and I don't understand what it means. So I'm just gonna trust that they did it correctly. The implications for the many worlds theory are unlimited. Just like there's an infinite number of combinations of particles in universes, there's an infinite number of possible physical laws ruling those universes. And maybe that's when we get all of the constants that govern our physics are defined, connecting the theory of everything to string theory and all of these other ideas that we just don't know. Maybe there's a universe where gravity behaves slightly differently, and then no stars or heavy elements are able to form. Maybe everything on the light spectrum is flipped. Purple is orange, blue is red, green is yellow, unless you're colorblind where it already is. Then there's the possibility that these worlds can also exist in a different number of dimensions. Maybe there's a world where everything is 2D. Maybe there's a world with a version of me that actually understands all of this. We don't know. If the many worlds theory is true, and to our understanding of math at the moment it is, then every single possible outcome is being played out all of the time. However, there is a distinction between everything possible in comparison to things that are impossible. A peach tree will never grow apples, and an apple will never not follow the rules of gravity. Does all this mean that there's a you and me out there that has made every decision differently? Or are there times like the peach tree where although we technically had a choice, every version of ourselves always made the same one? This theory basically states that if there's an opportunity to give you even a 1% chance of everything you've ever dreamed, in 1% of all of the universes, it will happen as long as you take that opportunity. But if you never take that chance, then there's no possibilities, no universes where that outcome occurs. Either way, for all of these outcomes, there are things that are more likely to happen. Just like that electron is more likely to be in some location than others. Because I read too many books and I am a hopeless romantic, I couldn't help but think, is that how we define soulmate? Are they the people we surround ourselves with the most often, whether it be a significant other or friends or whomever? Does that make them any different than the connections we make on a whim? People we meet despite everything in the universe screaming we shouldn't? Or is it even more amazing that, despite all odds, you were able to meet them? I don't know. Maybe instead, it all means that for every universe, no matter who they are, the people you're surrounded by are the most perfect people for you, because everything has happened in that universe to bring you together, even if that means no one at all. And if that's true, then is it any different than if there were no other universes anyways? Beats me. I mean, we spend all this time researching, and we're basically no closer than the day we started. So maybe we will never know, and maybe it's out of our grasp as human beings. And maybe there is no multiverse. But if it is real, and there is a multiverse, and there's a million different me's all living out their lives as every single possibility that could ever happen, I hope I love what I'm doing in every single one of them. And I hope that this reminds you that you should love what you're doing as well. Because even if there are 1,000 different universes, we're in this one. And all I know is that out of everything, I'm glad we're in this one, and that the laws of physics or whatever else brought me to the people I am with now. Because there's just not a universe I could imagine myself in without them. And maybe none of it matters, and maybe there's a universe where none of this is true. But what exactly does theoretical physics know about love anyways?